Welcome, and in this lesson, we're going to talk about Amazon Elastic MapReduce, also known as EMR. Now, as a basic understanding for the associate level exam, we need to understand a little bit about Amazon Elastic MapReduce. Now, here's the thing, this is actually a relatively advanced concept. In fact, really, you need to have a pretty good understanding of a MapReduce already in order to really take good advantage of this on Amazon Web Services. So my goal here and my job here today is to provide you with enough basic level information to prepare you if for some reason you have an Elastic MapReduce cluster inside of your environment, or you've been tasked with assisting developers in creating an Elastic MapReduce environment, or if you're preparing for the associate level exam for AWS. So, Amazon Elastic MapReduce is a service which deploys out EC2 instances based off of the Hadoop big data software. EMR, Elastic MapReduce, is used to analyze and process vast amounts of data. This data is generally unorganized data, and there's lots of it. For example, a text file that's 5 gigabytes in size that contains a ton of information, maybe logs to your website, maybe customer purchases, things that are not already organized inside of a relational database that we could query to find information on. We want to use this to find information and trends within a large amount of data. The most common used example when trying to teach MapReduce is something called word count. In this word count application, you have a giant text file of words, and your goal is to write what's called a mapper that goes through and categorizes the number of words or occurrences of each word and then sort them by the number of occurrences. So think of it in terms of that when we're learning about Elastic MapReduce. Think of it in terms of just a file of data, essentially, that we're looking at most commonly. There's other ways of doing this, but again, we're looking at this from a basic, most common level in order to be prepared to be architects. Now, the data is mapped to a cluster of Hadoop master and slave nodes for processing. It allows for computations to be performed by the servers or the nodes. These are the slave nodes. And the computations are performed in what are called mappers and reducers. And these mappers and reducers are logic that's created or coded by a developer. This logic is code that's looking for specific occurrences of an individual word. And that's the mapper's job. The reducer's job is to take that result, if there is one, and reduce it to a single output set of information. So if you have a single file that's receiving this information, the reducer is supposed to update that file with the most recent information from a mapper. So EMR from Amazon is built to run basically any open source application built on top of Hadoop. We have Hive, we have Pig. All of those are compatible with Amazon Elastic MapReduce. So a few key things about MapReduce, about EMR, is EMR launches instances for processing of the Hadoop software. In fact, all EMR does is launch a pre-built Amazon machine image with the Hadoop software on it. What does this mean? This means that if it just launches EC2 instances, it gives the architect, the admin, the sysadmin, whomever, ability to log into the underlying Linux operating system. This is unlike RDS. So we know that the EMR, because of how EMR works, because it launches EC2 instances, we know that we can have access. We have our PEM key, and we can log into these underlying operating systems. It integrates with services such as S3, DynamoDB, and Redshift. Redshift, a petabyte scale data warehouse, and it allows it to receive and output data to these locations. Now, Bootstrapper's utility built within the EMR that enables the ability to pass configuration information to the Hadoop cluster before Hadoop starts when a new cluster is created. So again, understanding how EMR works is a tough concept for people who have never been exposed to it. So EMR is made up of really mappers and reducers. These mappers perform your execution of logic. They're the things that go in and perform the execution on a chunk of data. Now, mappers are essentially the process that split the large data file for processing and then process it. Reducers take the result of that processed data, if there is a result, and combines it back into a data file on a specified disk, like Amazon S3, or the Hadoop file system, which would live on an EBS volume on the cluster. Now, let's look at this. This is an actually example from an AWS white paper. What we have here is we have our big data file. Like I said before, data is going to live in large file sizes. Think of this as a data of just arbitrary plain text of words. What's happening here is you can't load a 512 memory file into Elastic MapReduce and expect it to complete in any time quickly. This applies especially for larger gigabyte size files, right? It's broken up. Elastic MapReduce, the Hadoop, is broken up into chunks. It takes a chunk of the file. Now, these chunks can be 64 megabytes or 128 megabytes in size. Generally, it's already pre-configured by AWS, but we have the ability to change the chunk size, and this is called our input split size. So what Hadoop does is it chunks out this information, so it creates these chunks. Then it takes this chunk of 128 megabyte in size and loads it into what's called a map task. This is our mapper. A mapper lives on an Amazon node within the cluster. This is Amazon Elastic MapReduce. Now, there's only a specific number of mappers on an EC2 instance. We can configure the EC2 instance to use more mappers, but AWS already has it configured what they consider to be the optimum size for the optimum number of mappers per instance. So what the mapper does is it loads the 128 megabyte size chunk into memory and begins processing. So it begins processing against the code defined by that developer. That code is counting the number of occurrences for words within this 128 megabyte chunk. So that would be our mapper. It's the text being processed that's looking for the keyword. Now this is our word example. This could be a lot of different stuff. We could be counting the number of occurrences on a log file for a specific browser. As soon as that map task is completed, the reducer takes the result and updates the output result file for viewing. That result file can live on the Hadoop file system or, for example, the S3 file system configured within the Amazon Hadoop AMI. So what happens is we can have parallel processing. If we were only able to take a 128 megabyte chunk at a time and we only had one map task, then we would have to wait for this chunk to be done and for it to load another task. So this takes longer for processing. But what we see happening here is we have multiple chunks being created and multiple map tasks processing each chunk in parallel. So this means we're using either larger instance sizes or even larger instance sizes and more nodes within the cluster. So if a single instance can have 2 mappers and we have 4 chunks, then we might launch 2 nodes within the cluster that can process 4 chunks because it has 4 mappers at one time. Process with a whole bunch of data within 10 or 15 minutes and shut it back down again. So for performance, mapper tasks need to be loaded into memory as much as possible. If our chunk size is greater than our available memory on the system, then Elastic MapReduce has to write that information to disk and go back and forth. If it's loaded into memory, it can compute everything within memory and then reduce the output. Else, it has to use disk I/O to store specific results or to store parts of this 128 megabyte chunk on the system and read and write it and do the computations that way. So as I mentioned before, AWS EMR has already pre-configured the Hadoop AMI to have the best possible performance based off instance size. Technically speaking, you can change the number of mappers. If we were to change the number of mappers on an M1 small, we might not have enough memory, and that would decrease our performance, increasing our job runtime. So let's take a look at this. An M1 small has 2 mappers, 1 reducer. An M1 medium has 2 mappers, 1 reducer. An M1 large, 4 mappers, 2 reducers. Our M1 medium might have more CPU power, so the amount of time it takes for a mapper complete would be better. It might have more memory, so the amount of data that we can load into each mapper is higher, right? So that's how instance size affects our EMR cluster. So a single mapper is configured by AWS to handle, pre-configured depending on the Hadoop AMI, either 128 megabyte or 64 megabyte split files. This is default in the certain versions depending on which AMI you launch within the AWS cluster. To increase performance, you can adjust the split size on the file, but adjusting the split size might require more mappers to be started. So if we say, hey, we're going to take the chunks, and instead of 128 megabyte chunks, I want more chunks in smaller size. Well, the more chunks we have, the more mappers we need to process in order to complete it faster. And we'll demonstrate this in a second. Split files are loaded into the memory for processing. We need to try to always make sure we have enough memory for split files to be loaded. And generally, AWS already has this configured for us. If there are 5 128 megabyte split files waiting for mapping, then AWS will queue the ones not being processed, which increase the amount of time for a single job. So if we have 5 128 megabyte split files and we run a 2-node cluster of M1 small, that means we have 4 mappers. That means we can process 4 128 megabyte split files at one time, and 1 will be queued until a mapper is completed. So ideally, we want to try to do it in a way that completes in the fastest amount of time possible. A cluster can launch multiple instances for parallel processing, reducing the amount of time a job takes to complete by processing multiple split files with a mapper at one time. So the goal is to use as many mappers as you can without running out of memory for loading your data on an EC2 instance. If your job is queuing up, it can increase job runtime. Here are a few considerations. Determine if you have unused mappers. If you have unused mappers and you have a queue, then you might consider changing split size. So if you have 2 mappers that are being used and 2 mappers that are not being used, maybe consider changing the instance size or changing your chunk size. If your chunks are smaller, then it will use more mappers. If your chunks are larger, it might use less mappers. All depends on how much data you have and your chunk size and the number of available mappers. If you do not have unused mappers, but you have a lot of chunks in the queue, you can think about speeding up the process by adding more mappers, which is adding more core or task nodes to the cluster. We can automate this by using Amazon CloudWatch. We can look at how many tasks or chunk files are waiting to be processed. Both of these methods would be considered as increasing the number of available mappers. We know that when we increase the number of available mappers, if we have items waiting in the queue, it's going to increase the performance and decrease the job processing time. So let's take a look at our example here. We have a 256 megabyte size file stored, let's say, on Amazon S3. This file is then taken and broken up into chunks. Our chunk sizes here are 64 megabyte size chunks. It could be 128, so we could have a 512 megabyte size file. Then each chunk is sent to our mapper. We have an instance with a mapper in it for processing. Because our chunk size are 64 megabytes in size, because we have 4 mappers between our 2 EC2 instances, and because our file's 256 megabytes in size, we can process all chunks at the same time. This is called parallel processing. So we can spin up our cluster, process the chunks, and spin it down. This means our job time will decrease substantially. What happens if we remove one of these instances? We have 4 chunks and only 2 chunks can be processed at one time. So what this does is it then queues our items. So after these items are done processing through the mapper and being outputted with our reducer, then these will be processed. So this effectively doubles our processing time. So we have split files that are waiting to be mapped, which increases job processing time. And we can solve this by launching new cluster nodes or changing our chunk size. Now let's take a look at, again, the workflow. The workflow here is we load the data into our cluster. This can come from Amazon S3. It could come from DynamoDB or Redshift. This integrates well with other AWS services. We can load the S3 as a local file system, which actually increases performance and decreases job loading time. So if we use the local HD Hadoop file system on the cluster, when we shut down the cluster, we're going to lose that data. So if we want to create persistence, we can use S3. We can also use S3 for reducing job load time, because our output will go back to S3 and our input will come from S3 directly, rather than having to copy it to and from the Hadoop distributed file system. So then after we load the data, it's analyzed by our mappers, which are programming and scripts. Master node tells the data where to go and who's going to manage it. So we have a master node, core node, and a task node. So once it's done analyzing the data, the results are stored either on the Hadoop file system or the S3 file system, which is faster and has persistence. Then we can read the results from the cluster HDFS, Hadoop file system. Again, we could also read it from S3. It means reading the output from all of our reducers, our output file from our mapper conditions. So the master node only provides information about the data, where it's coming from and where it should go. The core node processes the data and then tells it where to store it. So it either stores it on the Hadoop file system locally or on Amazon S3. A task node processes the data and sends it back to the core node for storage. The task node does not run any process that stores the outputted information, so it only processes the data. The Hadoop file system stores the reduced result on the local file system, which means the data is only persistent for as long as the cluster is running. Once terminated, the data is lost. Storing the reduced data on S3 helps create persistent storage and reduces the amount of time it takes to copy the data from the Hadoop file system storage disk to the original location. So there is an action called Bootstrap Action. The Bootstrap Action can be used to install additional software or change configurations before Hadoop starts on a new EMR cluster. One thing that we should consider using is using S3 as the local file system, as it directly connects to S3, and enable multi-part uploading for faster uploading and processing of data to and from Amazon S3. By default, the S3 file system is already installed on all nodes on a cluster. However, if we want to enable multi-part upload, we can configure that in a Bootstrap action. Using S3 for the primary file system with multi-part upload enabled decreases the job runtime and provides persistent for your cluster. And of course, we know S3 increases durability of your reduced data. So that concludes it for this lesson. We had to cover a lot about Amazon Elastic MapReduce. We had to understand a little bit about what MapReduce does. So what we need to be sure to take away is if we have an Elastic MapReduce cluster running in our environment, we need to be sure to understand what that architecture looks like, what can affect performance, what we have access to as architects and administrators. So that concludes it for this lesson. Go ahead and complete this lesson. So one question we might ask ourselves is, how could EMR be used within an application environment on Amazon Web Services? So we know we can use it to analyze data that we already have, but how could we use it to analyze data as it relates to our environment? Well, we could store Elastic Load Balancer logs on an Amazon S3 bucket, and then we can use EMR to process those log files and look for trends in that data. What URLs people are accessing, errors, what browsers they're using, what version of desktop are they using, is it a mobile device? So we can process all of that data with EMR, and it's an absolutely great option for using that within our environment. So that concludes it for this lesson. Go ahead and complete this lesson and move on.